Welcome to Part 4 of our Data Literacy 101 overview. In this video, we explore reading data. What do you think is meant by reading data? Is there a secret code? Do we need an interpreter? Reading data in the context of data literacy is more than just interpreting words and symbols. In many respects, it begins with determining if you can trust the data. We can do everything right to clean and understand our data, but fail in our analysis because the data are not trustworthy. Let's look at some of the ways our data can be trustworthy. Accuracy. Are the data correct? Does it accurately represent what it says it does? Based on data collected from HRC years ago, it appeared that a majority of Army officers were in the top 10% of their respective year groups. How could this be? At one point, senior raters could write so-and-so is in the top 10% on every evaluation without restriction. The evaluation was reformed, as it has been several times before, and the narrative block and the block check may still not match, but at least 51% of officers are no longer part of the most qualified, right? Complete. Are there missing values? What do we do about missing values? How do we use the data to impute values? Do we filter them out? Can we reach back to the source? If a data set is incomplete, we need to understand why data are missing. Consistency. Does the type of data change? Consider survey data that allowed free response for age. While most of the data was numeric, such as 10, 23, or 57, some of the data reported included old as dirt or lived with dinosaurs. Uniqueness. Do we have duplicate entries? This may double our counts and make our analysis misleading. If we have this information already, then we may be wasting time and resources. Timely. The data and analysis need to be available and complete before the decision is made. Similarly, one should be mindful of data that has an expiration date. This is why during planning we make note of LTIOV, the latest time information is of value. Take a few moments and look at this picture of what appears to be a spreadsheet. Do you know what you're looking at? This image depicts raw CGSS Army change of command shortages data from a .txt file. It's not easy to read or interpret, but technically it is data. So what are data? We've been introduced to multiple definitions so far in this overview. From a practical standpoint, let's just think of data as a series of facts suitable for analysis. You've already been introduced to various types of data and the levels of measurement, and there are indeed many different types of data. In broad strokes, we have numerical, categorical, unstructured, and two special data types that we will handle a little bit differently, called temporal and spatial data. This list of data types is not exhaustive. However, this is a good place to start a conversation about reading these different types of data. Numeric data, as you may have guessed, is about numbers, and we can classify numbers as discrete or continuous. Discrete means our numbers are finite or countable. In other words, they are whole numbers, such as someone's age or the number of people in a class. Continuous numbers can be expressed as decimals, such as someone's height. Water, or H2O, can be quantified either way, depending on its state. Ice cubes are discrete, and we count them. Liquid water, and steam for that matter, are continuous, and we can measure their respective volumes or mass, as the case may be. The rules of grammar help us out in this respect. You can have less water or fewer ice cubes, but not the other way around. In the same way, you can have fewer 155 millimeter artillery rounds and less ammunition, but you can never have less 155 rounds or missiles or tanks or kernels, for that matter. Categorical data refers to a fixed list of things. It can be ordered or unordered. These subcategories are synonymous with the ordinal and nominal measurement scales, respectively. Rank is a great example of the former. A major in 04 is ordered higher than a second lieutenant in 01. Even though ordered categorical data often appears numerical, try adding 4 second lieutenants together to see if they add up to 1 major. Also, if you work with survey data, you might see ordered Likert categories such as agree, disagree, neutral, strongly agree, all that stuff. There are ways to express categorical data as numerical data. So suppose we have 4 candidates who've either passed or failed Ranger School. In this case, there are only 2 options for this data. You can pass or fail. So we can express pass as the numerical value of 1, and we can express fail as the numerical value of 0. Likewise, we could create a column for every MOS, and assuming each soldier has only 1 primary MOS, we can tally up, or this way measure the frequency of each job specialty. Unstructured data is a type of qualitative data. In computer programming or data science, words, numbers, and symbols may occupy string fields, and a string is a sequence of characters, usually of a fixed length. In surveys, this is usually represented as a free text field. Finally, there's special cases. We call them special because we must pay attention to their format and how we use them for analysis. So this is temporal data, and of course it refers to dates and times. And then you have spatial data, which refers to a specific geographical region or area or location, normally using map coordinates. And spatial data typically describes or falls into 3 categories: a point, a pathway, or a region bounded by some sort of polygon. Now let's look at some network traffic data. By the way, when you receive a data set, it might be important to request a list of terms to help explain the meaning of each data column. Often, though, we just have to figure it out. So let's look at the column headings. Can you identify the types of data for time, source, destination, protocol, and info? Time is temporal. This format may be unfamiliar to you, so you'll need to decipher it first before you decide to use it. Source and destination are categorical. You may have been tempted to call these numerical, but numerical values have a natural ordering to them. So even though they look like numbers, these data actually represent Internet protocol addresses, and every computer has a unique one. Protocol is, well, it's obviously categorical. And info appears to be unstructured. Being able to differentiate these types of data helps us communicate with data professionals. Our techniques and approaches to analysis will be different depending on the types. It will help us recognize the need to clean or reformat the data as appropriate. Sometimes our data has a clear structure. Consider this table. the data appear to be well formatted and ready for predictive modeling. In this case, we are focusing on the BMI column, which is a continuous numeric variable. And we're going to use that to predict the physical injury column, a binary numeric variable where 0 equals no injury and 1 equals injury. You may notice that this snapshot only includes people with no physical injury reported. The full data set includes people with reported injuries as well. Otherwise, our very simple model would classify every person as no physical injury regardless of BMI. A few years ago, the public affairs officer of the 75th Ranger Regiment asked an operations research systems analyst, an ORSA, to analyze Twitter data. The goal was to determine whether the sentiment towards the regiment was generally positive or negative. This slide shows a snapshot of the collected Twitter data, including tweets mentioning the Rangers and the Army, along with metadata such as user information, tweet content, and engagement metrics. Our client, the Ranger PAO, is interested in understanding public sentiment towards Army Rangers based on this social media analysis. Continuing our examination of 75th Ranger Regiment Twitter data, the PAO wanted to analyze the sentiment towards the regiment, and besides the tweets mentioning the Rangers and the Army, we also have been provided with usernames, timestamps, search terms, locations, follower counts, and favorite counts. As the PAO considers these data, he must identify the different data types present in this data set and think about what additional information might be useful for his analysis. This data helps us understand public opinion and engagement with the Ranger Regiment on social media. So what else would you want to know for a comprehensive analysis? How can we better present these data to make things more readable? This involves thinking about formatting, structuring, and possibly visualizing the data for a clearer understanding. I mean, we could create a word cloud just from the text messages. We could organize the tweets into codes and themes. We can show the relative impact of these codes and themes based on the number of followers each sender has. We can create a heat map, in this case, showing the effects or impact of these tweets across the country. So what suggestions do you have for improving the readability of this data set? How can we present this information in a way that makes it easier to analyze and interpret? This slide introduces a data set with special data types, specifically COVID-19 statistics by county in Alabama. Each row represents a county and includes data points such as the date, the FIPS or Federal Information Processing Standards Code, county name, state, country, and counts of confirmed cases, deaths, recoveries, and active cases. Special data types like this are used to capture detailed and specific information for in-depth analysis. These data types are often structured to allow for granular insights and targeted decision-making. This slide presents a data set of notional unit ACFT scores. Each row represents an individual with attributes including their company, gender, age, NTC participation, BMI, and of course the ACFT score. The purpose here is to assess whether these data are ready for prime time. As we look at the data, consider aspects such as completeness, accuracy, and consistency. Notice discrepancies like a score of 0, an unusually high score, or missing or unclear values. In this case, look under the NTC column. These observations lead us to a question. Are these data ready for analysis and decision making? What steps might be necessary to clean and validate this data set before using it for any substantial conclusions? Standing on the Schleich, Doctrine Man, Master Sergeant Half-Mast, and of course, the Force Management guy, the time has come for a new hero. Introducing Data Boy, whose mission is to find and clean up raw data everywhere and combat the evil forces of Dr. Disinformation. Okay, seriously though, we should get ahead of this. I mean, everyone else is doing it. Okay, well, let's move on to data wrangling. It turns out that raw data sets are rarely packaged in a format that is immediately useful and ready for further analysis. Even if the dataset is error-free, we usually reformat it to suit our purposes. Data wrangling is the process of transforming raw data into something you can use. Data cleaning is an important step within data wrangling. Cleaning data consists of removing inaccurate or unreliable data. These terms are often confused or used interchangeably, and regardless of your position on that, remember that it's all about preparing your data for analysis. Consider the column containing these entries. The computer reads these as 4 separate groups due to inconsistencies in naming conventions. Such structural problems can distort analyses and insights. Addressing these issues involves standardizing data entries and removing duplicates to ensure clean and reliable data for accurate analysis. On the slide, you can see images of houses, with one house significantly larger than the others. This visually represents the concept of an outlier, where the large house is the outlier compared to the smaller, more consistent houses. An outlier is a data point that is significantly distant from other observations. It can skew and distort statistical analyses, leading to misleading conclusions. So, what should you do when encountering an outlier? Well, we can remove data points that are clearly errors or impossible values. We can conduct analyses both including and excluding these outliers to see if they affect the results. This helps determine the robustness of the findings. We can use statistical techniques to control for the influence of outliers when performing regression analysis. This ensures that outliers do not disproportionately affect the model's results. Let's talk about missing data. It's important to distinguish between zero and missing values. Missing values indicate that a score, such as a fitness test, wasn't taken, and these are often coded as NaN or some similar placeholder. Zero values, however, could represent a failed test. Analysis tools will treat zero values as actual scores, not missing data. So this distinction is crucial to avoid incorrect conclusions. Additionally, watch for incorrect coding. Sometimes missing values are incorrectly coded as negative numbers, like -99. These should be converted back to standard missing value markers to ensure accurate analysis. Proper handling of missing data is essential for reliable results. Another framework for assessing the results or findings drawn from data is through research validity and reliability. Validity refers to how accurately a method measures what it is intended to measure. For example, construct validity. Does this measure the intended theoretical construct? Internal validity. Are the results attributable to the variables being studied? External validity. Can the results be generalized to other settings, other populations, other times? Reliability. This refers to how consistently a method measures something. For example, test-retest reliability. Will testing the same group under similar conditions at different points in time produce similar results? Inter-rater reliability. Do the observations or observers agree with each other? Internal consistency reliability. Are measurements consistent? Do they measure the same construct? Understanding these concepts helps ensure that data collection methods produce accurate and consistent results essential for making valid conclusions. Here's an illustration for you. This image will help you visualize the relationship between reliability and validity using these target diagrams. Now this is kind of simplified, but just go with it. So for the target on the far left, that's reliable but not valid. Well, as you can see, we have consistent results, but we're not hitting the target. On the next target, low validity, low reliability, inconsistent results again, and still not hitting the target. The third target over from the left, reliable, but not valid. Well, you have results scattered around, but they're kind of grouped together, but you're missing the target. And then finally, we have reliable and valid. So these are results that are both consistent and accurate, and you're hitting the target. So these visualizations highlight the importance of achieving both reliability and validity in data collection, which will affect the analysis methods to ensure the most accurate and dependable findings. Let's talk about lurking variables using a simple example. We see that increased ice cream sales are highly correlated with shark attacks. At first, this might suggest a direct relationship between the two. However, this correlation is likely due to a lurking variable, something that impacts both ice cream sales and shark attacks. Confounding variable is another term often used interchangeably with lurking variable. So the key question to answer here is, what could be impacting both ice cream sales and shark attacks? This slide illustrates an example of a spurious correlation showing the relationship between the number of letters in the winning word of the Scripps National Spelling Bee and the number of people killed by venomous spiders from a time frame spanning 1999 to 2009. And despite a visual correlation, there's no logical or causal connection between these two variables. In this scenario, there are no lurking variables affecting the number of letters in the spelling bee or spider-related deaths for that matter. Instead, this is a classic case of spurious correlation, where the relationship is purely coincidental. The two variables are independently influenced by completely unrelated factors, making any apparent connection between them meaningless. Spurious correlations occur when two variables appear to be related, but the relationship is actually caused by a third variable or is purely coincidental. For example, here we have Nicolas Cage, and the number of movies that Nicolas Cage appeared in appears to correlate with the number of swimming pool drownings during a particular time frame, year or years, across the country, I guess. So this is a classic coincidental spurious correlation. There's no causal link between Nick Cage's movie appearances and swimming pool drownings, and there's no variable that would explain that either. There's some other ones like this. For example, margarine consumption and divorce rates in the state of Maine. per capita cheese consumption, and number of people who died by becoming tangled in their bed sheets. Let me say that again. Number of people who died by becoming tangled in their bed sheets. I really had no idea there was such a thing. Okay, so we've used the term variable quite a bit now, and let's look into what we mean by variables. So you're already familiar with dependent variables and independent variables. IVs are said to explain DVs if statistical analysis demonstrates a significant relationship. So now on your screen, I'm going to list some other classifications. So for example, control variables. These are variables that are kept constant and controlled by the researcher to prevent them from influencing the outcome. So an example might be a study examining the effect of a new drug on blood pressure. So you'd want to control for things like age, diet, physical activity of the participants, of course. Extraneous variables, these are variables that are not intentionally studied, but they could still influence the results. So in a classroom experiment on teaching methods, extraneous variables could include the time of day. Is it AM or PM? Is it right next to lunch? I don't know. Or the classroom environment. Is it crowded? Is the AC or heat working that day? I don't know. Confounding variables, these are a type of extraneous variable that varies systematically with the independent variable and can affect the dependent variable, potentially leading to incorrect conclusions. So consider a study on the effect of exercise on weight loss. A confounding variable could be the participant's diet as it affects weight loss. Moderator variables, these are variables that influence the strength or direction of the relationship between the independent and dependent variables. So an example might be a study on the relationship between stress and health. Social support could be a moderator variable. So maybe you have a strong, you belong to a strong, close-knit church group or extended family or something like that. And that's all we're going to talk about here. There are others, but you need to take these into account because proper handling of these variables will help ensure that your study of the data is more accurate, reliable, and valid. Here's some guidance on how to be a critical consumer and of data and research findings. You probably already are aware of Occam's razor. Start with the simplest explanation, and often the simplest solution is most likely to be correct. Be aware of spurious correlations. You definitely want to check the axes on any graphs you see. See how they're numbered. Maybe the numbers are extended or compressed for some reason, and it has the effect of distorting the data. We've already talked about lurking variables. Sampling method size and representation. Here's where you assess if the study sample is representative of the population. So, a study consisting of a sample of a staff group, or maybe a couple staff groups of ILE students, and you took some, you gave them some surveys. Well, it could probably be said that the results of that analysis would not be generalizable to the entire Army for obvious reasons. Okay, and before that, study sponsorship motives. So you got to consider where who's pushing this research. Maybe it's a private company that's funding it. For us in the Army, it could be another command, it could be a sister service, it could be any other entity, and maybe that entity has some leverage on our organization. I don't know. People can look at that and point and say, well, this sponsor has a vested interest in the results, which could mean there's some bias. But anyway, the burden of proof is on the researcher, is on the person who's pulling the data, gathering the data, and analyzing it. And it's not you, unless you are the one who's doing that. Let's work under the assumption that you're not the data analyst here. So it's crucial to critically evaluate the outputs, the research, the findings, to ensure its validity and reliability before accepting its conclusions. So we've covered key aspects of reading data. We've talked about different types of data, introduced a few more for you to consider. Talked about making data readable. This goes back to data wrangling, cleaning, transforming, visualization. Validity and reliability, we talked about that. Pitfalls in data analysis. This is where we talked about spurious correlations and bias. Common variable classifications. We just went over that. Independent, dependent, continuous, categorical, control, those things. And being a critical data consumer. So bottom line, you got to evaluate your data sources and methods critically, because mastering these areas will enhance your ability to work with data effectively and make informed decisions. Okay, next up in our overview of data literacy, we communicating data.